Welcome to calculus. Fractions will pop up when you least expect it. On this episode, Stevenson will demonstrate physics and calculus go hand in hand like yin and yang, like peanut butter and jelly, like milk and cookies. If you've already taken physics, you're going to hear some things probably you've heard before. If you haven't taken any physics at all, don't sweat it, I got you covered. So here I have for you is one of the tree maps, from the website. I'm going to very quickly go through this. The yellow tree branch there is meant to talk about position. Position is just the location of some object with respect to time. Now, what that time frame is and how you define the location totally depends on the problem. So don't assume it's a one-size-fits-all. Green branch, velocity. Velocity, if you notice, is just the derivative of your position function. So velocity gives you the direction and magnitude of an object that is moving with respect to time. So direction and magnitude is a vector.
I'm applying for a new villain loan. Go by the name of Vector. It's a mathematical term, a quantity represented by an arrow with both direction and magnitude. Vector! That's me, because I'm committing crimes with both direction and magnitude. Oh yeah!
With our velocity, because of the sign of it, it'll tell us what the direction it's going. Is it moving left, up, down, right, backwards, forwards? All of that depends on the context. And the most important thing is that when your velocity is 0, the object is at rest. The red branch is all about acceleration. Acceleration is actually, look at this, it's actually the derivative of velocity. But wait a minute, velocity is the derivative of position. That means acceleration is the second derivative of your position function. Acceleration is also a vector. However, it's talking about the direction and magnitude of the rate of change of the object's velocity. So we're talking about how is the velocity changing. Last branch is the blue one is speed. The speed is basically how fast is something going regardless of direction. The perfect example of that is your car. When you get in your car, and whether you put it in drive to go forward or reverse to go backwards, your speedometer behaves exactly the same way. Why? Because it's telling you how fast you're going. The direction is irrelevant. The second tree map are the following. Displacement, the orange one. Displacement essentially is just how much distance did your object move over a time frame. Again, how you measure that depends on the context of the problem. Average velocity, the teal one. Average velocity should sound very familiar. All it is the average rate of change, but instead of your denominator being two random x values, it's just time. Speeding up or slowing down. When you're looking at trying to determine if something is speeding up or slowing down, essentially what you want to do is look at the signs of acceleration and velocity. Remember, they're vectors, so they're going to have a sign. If their signs are the same, your object is speeding up, it doesn't matter if they're both positive or negative. But if their signs are different, then the object is slowing down. The last one is changing direction. Now remember, velocity gives you direction of your object. All right, so if you want to know when an object is changing its direction, like say, hey, when does it switch from going left to right or forwards to backwards? You're looking at the signs on velocity and where it switches. But first you need to look at the zeros of your velocity graph or equation, and then decide, does it actually change sign? So you may be wondering, why do we need all these vectors? What are these? So here's a really quick example of vectors for you if you were not in a physics class or if it's been a while. So suppose this graph here represents the position of some object being shot up into the sky, okay? So S of t just represents height and t is time. How would you describe the object's position with respect to time? So we would look and say that the object starts at 0, and as time is increasing, we can see its position or its height is increasing. It reaches a maximum height of 6.25, whatever the units are, meters, feet, miles. And then it comes back down at 5, whatever the time is, seconds, minutes, hours. How would you describe the slope at the following points? So look at A. Could we say that A was probably like a positive, right? B is probably positive. C is going to be horizontal, so that's 0. D is going to be negative, and E is going to be negative. What we're doing now is when we describe those slopes, we're talking about velocity. Remember, because the velocity is the derivative of position, and derivatives is the slope of the tangents. Now, you see my little vectors? I know, they're cute. What happens if we apply acceleration? Remember, on Earth, we have gravity. So we always have this acceleration due to gravity. The thing is gravity forces us down. See all my little red vectors? Everything is down. Think about a moment ago when I talked about whether something's speeding up or slowing down, right? Signs are same, signs are different. Why is it that an object from 0 to about c seconds, why is it going to slow down as it gets to the top? What do you notice about the vectors here? Do you see how they're opposing themselves? See, the acceleration is always down. So if you think about it, when something shoots up in the ground, eventually it's slowing down and it reaches a maximum height. That's because the sign or the direction of the vectors of acceleration are opposing or different than the signs of your velocity or your vectors of velocity. And there's a tiny moment where it hits that highest, maximum height, and then it's going to start falling. But here's the thing, when it falls back down to the ground, it's not at a constant rate, it's accelerating. And that is because it's going to be speeding up, because look at the vectors. Do you see how they're both headed in the same direction? That's why the impact at ground will not be constant from where it was falling before. So this is just a little illustration of how we use vectors to demonstrate speeding up or slowing down.